Hello everyone, I'm Ravindran and I'm a professor of computer science at the Indian Institute of Technology, Madras, popularly known as IIT Madras. And I also head an interdisciplinary center on data science and AI here, the Robert Ward Center for Data Science and AI. So let's move to the slides. So today I'm going to be talking about some of our recent work on learning complex policies in deep reinforcement learning. So many of you are familiar with reinforcement learning, and one of the major challenges in reinforcement learning is you really need to be able to solve complex problem domains to explore the kind of learning challenges that humans face, in particular how we learn structured solutions to problems, right? And to explore effectiveness of such structure in policy space. So we need to work in really complex domains. Earlier, reinforcement learning was largely limited to small toy domains, with an occasional exception of a helicopter or a backgammon. But deep reinforcement learning nowadays allows us to look at really large domains. So some may argue that they are really large toy domains, but still it gives us sufficient complexity because this combines the feature learning power of deep networks with the trial and error learning of reinforcement learning. And the different neural architectures that people have bought to employ allow us to explore really different solution methods. And so I'll start off with a little motivating video to talk about why we need structure in policies. So this is the very famous the Atari game player from Deepmind. This is the earliest version of it. And let's skip ahead a little to demonstrate what I mean. So you can look at this. Now the agent is starting to learn how to solve the problem, but you can see that the way the agent is controlling the paddle doesn't look very natural. So there's a lot of dithering and a lot of unnecessary movements. And it's something that would be nice if we could address. And especially in domains where there are real physical constraints involved, you don't want this kind of jerky behavior. And let's just look at the video again. So we initially saw how it was learning to play the game called Pong, and right, and then so when you get it to learn to play the game Breakout, in some sense it has very similar dynamics to Pong, in the sense that you have a paddle that you have to slide across the screen and bounce a ball off. Right? But in effect, the agent literally learns things from scratch all over again. Right? And it's not able to, reuse parts of the knowledge that it had earlier. And even though it's using the same learning algorithm, the same architecture, it's a different copy of the network that learns how to play Pong, how to play Breakout. Right? Of course, there are solution approaches that try to address this, but still, it's always room for doing something more systematic. And lastly, there's this game called Sequest, right, which has a lot of structure in the game, in the sense that there are multiple objectives that the agent has to solve. The agent has to kill the enemies, it has to rescue the swimmers, right? And at the same time, it has to make sure that it doesn't run out of oxygen, which it fails to do that. So if you look at this, so it starts, now it's very good at killing the enemies, right? But it doesn't know that it has to pay attention to oxygen. Of course, it's not a trivial task because there's just too many things going on the screen, and it has to know that exactly these set of pixels correspond to oxygen. But the point is there are multiple objectives, and something that is a lot more structured would learn these policies much faster. Right? So having given that motivation, so let's look at some of the problems that we pointed out in the earlier video. So it's some kind of non-smooth policy learning that happens, right? And sometimes it's due to arbitrary choice of hyperparameters. Sometimes it's due to a lack of appropriate regularizers. And then there's a lack of structured policies. There is no notion of decomposition. So you don't think about breathing as a separate subtask while rescuing and killing enemies as separate subtasks. And we don't transfer policies, right? which is something that you would expect with deep learning because we have had reasonable success in feature transfer and supervised learning. And I would expect something similar to work with reinforcement learning, transfer of policies. And it's beginning, people are beginning to see successes, and I'm going to talk about one of the significant success stories that we have had. And then, of course, there is this problem of learning a single network, training a single network to perform multiple tasks. Like I was mentioning, many of these solutions that you saw were all trained independently. And some of the multitask solutions that are there in the literature are typically offline, where you train a network for each and every task, and then you copy all of those solutions onto a single network. That would mean that you basically have done the training individually for each one of those anyway. And then another problem that bedevils reinforcement learning is that of sparse reward information, because you don't, for every action you do, you don't really get a reward. So even in something like Pong, you might have to return the ball many, many times before you score a point because your opponent misses it. Right? And there are several other problems with both RL and deep RL, too many to get into at this point. And that's just some of the recent contributions that talks to these issues. So about learning structure in policies or in complex policies. So we have proposed a framework called Fine-Grained Action Repetition Framework, or FiGAR, which allows you to learn smoother policies by repeating decisions that you make and not changing the decision at every time instance. We'll talk a little bit in detail about that. Then we have looked at solution approaches for decomposing a more complex problem into subproblems. And then we looked at transfer learning, which again, an architecture called attend, adapt, and transfer. And I'll talk a little bit more about that today. And then we also have done quite a bit of work in online multitask learning. And this is also reported this year at ICLR, where we use active sampling to train a single network to solve several tasks simultaneously. Right? And we also have looked at other issues. So to address the sparse reward problems, we did some work on learning with richer information. So not just scalar reinforcement signals, but things like imitation learning and instruction taking, and also trying to build on classical control ideas where we use information about the domain and use RL to refine controllers on top of domain-based or model-based methods. And we also have done quite a bit of work in robust reinforcement learning, including something that was reported last year in ICLR. And so this talk, so I'm going to talk about three things. It's going to be a brief account, but enough detail. The first one was learning action repetition or fine-grained action repetition. The second one is on selective transfer learning, which we call attend, adapt, and transfer. And the third one, I'm going to talk about the online multitask learning setup or active sampling. So I'm kind of deviating a little bit from the announced abstract because I felt that I wouldn't be able to do full justice to the third topic that I had picked in the time that was available. So I'm going to talk about online multitask learning instead. Okay. So let's start with FiGAR. Right. This was joint work with a couple of my graduate students, Sahil Sharma and Arvind. And an early version was reported in AAAI, and then a later version in ICLR 2017. So if you look at the current deep learning methods, they tend to interact with the environment by choosing to repeat actions over a certain time period. This is done for multiple reasons. One is that processing load or overhead is reduced so that you're actually making decisions once every so often instead of at every time interaction, right? And typically the repetition factor that is selected is one of 4, right? This is something that was reported in one of the early papers on deep RL, and people seem to have stuck with 4 for a variety of reasons. And so the question that we set out to ask is, what if the agent can predict both the actions and the persistence of the action? So apart from the computational reason, there are also cognitive reasons to worry about this kind of persistence of action, because humans tend to not change their decisions that rapidly and tend to stick with decisions for a while before they actually change a decision. this is something that even if you think about it, I mean, you would see that you don't do this quite often, right? And here is another motivation drawn from the Atari domain. So there are some games like Freeway where your optimal policy is going to have large chunks of repetition. So here, look at this is go up for like 29 steps and go down 28 steps and so on and so forth, right? So this is like not just a action repetition of 4, but much higher action repetition. And Freeway is a simple game, but you could see the same kind of phenomenon happening in Sequest as well. So in this particular screen, your optimal action is to like go down 9 steps. And here it is to go diagonally down 9 steps so that you can reach this point, right? And likewise, you can see multiple repetitions. And here is a little more complex thing. It's go diagonally down to the right while you fire. And all of this is a single action in Atari action encoding, right? And you do this continuously for 9 steps. It could be something that you do for, cleaning out a line of enemies that are coming out to you. Things like that. And sometimes your optimal policy has action repetitions as high as 18. Right? And so it's very clear that action repetition of 4, while it might be a great single number to arrive at, it's certainly not optimal at all instances and across all games. Right? And so the idea here is that we not just decide on the action, but also how long you want to execute it. And this has connections to things like chunking that people have studied in behavioral psychology, where the humans tend to tend to group actions together and make decisions at the group level as opposed to individual action level. And this has been modeled in the oral setting as either macro actions or options and so on and so forth. And the policy decisions in this case could change less rapidly. And you make your decision-making granularity is significantly reduced. And you could potentially think of not just repeating single actions, but also a more complex subsequences of actions that allow for you to build more and more complex policies, right? And so what we set out to achieve with FiGAR was to give a lightweight framework, right? And the assumption is that you don't really need any additional information. Whatever observations you're making from the environment are sufficient for predicting the actions and their persistence. And we set out in such a way that this FiGAR could extend any of the deep RL algorithms that are out there. It could be A3C, DDPG, TRPO, whatever's your favorite deep RL algorithm, which explicitly maintains a policy. So that's the only caveat here, right? So the crux of the idea is to just modify the objective function so that you learn the action repetition distribution simultaneously with the action distribution as well. So for people who are familiar with A3C, just a quick recap as to what the objective function is. So you have two loss functions that you're trying to minimize. One for the actor, right, which essentially takes a log of the policy parameters and then times the advantage. And the loss function for the critic, which is just the square error loss function, where V hat is the target that you're trying to approximate, and V theta is the actual predicted value from the approximator, and V hat is essentially an end step truncated return, and n equal to 20 was something that was empirically used. Right? And so with the FiGAR A3C, what we did was we added an additional network. So if F theta A is the network that learns pi theta A, we just added another network, F theta X, which has the same parameterization as theta A, except that the final layer is a softmax of size 30 that gives us sufficient granularity to decide on what the repetition should be. Right? And so the loss function for the critic is more or less the same, and the loss function for the actor now is essentially the same pi theta A earlier, but also with the pi theta X. So the exact structure of it has not changed, except that we have added a loss component. And we can do something very similar for both DDPG and TRPU as well. Right? So we did evaluations on multiple domains. We did it on Atari suite, a suite of 33 Atari games. And we also conducted experiments on Mujoko, where we used the TRPU algorithm, and also on Torx, where we extended the DDPG algorithm. So with the Atari, we used A3C. So I should point out that in the Mujoko domain, especially when we are looking at learning walking gaits, we typically ended up learning action repetitions of one, because you really don't want to repeat actions when you're trying to learn the gait, and you really want to alternate so that you can get up a steady gait, set up a steady gait. And so that was something, but at least it's good to know that even if the action repetitions are not useful, our method does tell that. Right? So let's look at what happened with Atari games. So here is a statistic that we are plotting, which is a percentage improvement over the baseline A3C. Right, and you can see that for many games we get significant percentage improvement, including in some cases several hundreds and even thousands of percentages. And in some cases our performance is poorer than the baseline, but that's surprising because the baseline uses a repetition of 4, and we should be able to learn with the same, at least learn the same repetition of 4 on every frame. Maybe it just needs more experience and more trials, and we get to at least the same performance as a baseline, right? But it's interesting that we are able to learn much better policy, and I suspect the reason for that is this action repetition acts as an additional regularizer to the policy learning, and that allows us not only to learn a smoother policy but also learn more efficiently, right? And here is another figure that tells us that action repetition is truly useful, right? These are for different games, and the bars here tell you what fraction of the moves that were made in the game used a specific action repetition. So the more pink the bar is, that means the longer the action repetitions that were used. So for example, here in Freeway, about 20% of the moves used action repetition between 28 and 30. So that essentially means that many games we have large action repetitions. And then there are games like Atlantis where the bulk of the action were actually using a repetition factor less than 4. So this is between 1 and 3. Nearly 50% of the actions were between 1 and 3, and in Crazy Climber, more than 50% were between 1 and 3. That essentially indicates that 4 is not necessarily a great choice, even if you are not going to repeat actions a lot. Right? There are a few games like Tutankhamun where 4 to 6 was nearly 75% of the game. But in many of the games, you had varying action repetition factors. So one of the things to note here is that in very few games was a single action repetition factor dominant. Even in games where high action repetition factors were not very dominant, you could see that at different points in the game, different repetitions were useful. So this essentially tells you there's a lot more to explore and learn here than to look at the fixed action repetition. The nice thing about FiGAR is it's sufficiently lightweight that you could wrap it around any of your favorite learning algorithms and not with too much of an overhead. Right? So the next thing I want to talk about is attend, adapt, and transfer. And so and this is joint work with, again, a set of my master students, Janardhanan, Arvind Srinivas, and Prasanna, and a colleague of mine, Mitesh Kapra, who is also a faculty at IIT Madras. And so before we get into the transfer side of things, just a quick one-slide recap of what attention means. So attention mechanisms really help us to pick out salient information from the input. So, for example, here you see a picture where a woman is throwing a frisbee in a park, and the network is trying to generate a caption that corresponds to this picture. And when it generates the word frisbee, it really needs to look at those pixels that are brighter here, right? It really needs to focus on these pixels and not on the rest of the image. And therefore, this allows this kind of attention mechanisms let you pick out parts of the input that are needed for deciding on a certain output. Right? And so this allows us to look at a much larger context in the input, but without getting distracted while solving the problem. Right? And here is a one-slide explanation of what we mean by transfer. So suppose you know how to play a racket sport, and maybe you can use that knowledge to learn to play another racket sport faster. And now, before people who know major tennis fans and squash fans pile on me, I do know that these are really very different games, and this is just for illustrative purposes. Right? So you have squash, and then you could potentially play tennis a little faster. Likewise, more less controversial example, suppose you can play breakout, and then maybe you should use that knowledge to play pong faster, because it's all about sliding paddles and hitting balls, right? But then we're interested in a slightly more interesting question than just transfer, right? We want to see if we can do what we call selective transfer. So let's say that you have two experts play tennis, but then one has a backhand that is much, much better than his forehand. Another one has a forehand that's much better than the backhand. What I would like to do is transfer the backhand from one player and the forehand from the other player. And well, I should point out at this point that I believe the player on the right actually has one of the most perfect games in the world. And this slide was prepared by a graduate student of mine. And so what is the motivation in transfer learning? So it's to speed up learning on new tasks by using past experiences on related tasks, right? And so the questions that we are asking is, how do we identify if a source task is suitable and appropriate, and where it is appropriate? This is the selective transfer part, right? So I don't just use a source task in my target task, but I try to figure out where exactly in the target task it's appropriate. And the second question we want to ask is, how do we prevent what is called negative transfer, right? So negative transfer happens when I'm trying to copy from an expert, or trying to do transfer from an expert who's not entirely appropriate for the target task I'm trying to solve. And in which case my learning could slow down, right? The optimal performance they achieve could be affected, and so on and so forth. And any of these effects is called negative transfer. So how do we prevent negative transfer? And how do I do selective transfer? So these are two questions we set out to answer. And here is a simple architecture that we use. We call it the A to T architecture. And so you have a set of experts. You can see that the stack of green networks on to one side, right? These are could be the policy networks, could be the queue networks of n different source tasks, right? And I have an attention network, right, which learns weights for each one of these value functions. This is an attention weight. So basically, it tells me which one of these expert tasks I should pay attention to. So this allows me to do the selective transfer. So it says that, hey, if my first policy's weight here is 1 and the others are 0, then I'll be paying attention to the first policy. Right? So, but then notice that this can actually be a non-binary vector, in which case I'll essentially be taking some kind of a weighted combination of the value functions, and I'll be making my decision based on this final value function, right? And but then I need this allows me to transfer from more than one expert, and then choose which expert to transfer from, because I have the state signal. But then how do I avoid the negative transfer? So I have a base network, right, which is essentially learning to solve the problem from scratch without worrying about the experts, right? And the attention weights, they could also potentially have an entry for the base network. And if all my experts are failing, I would eventually transfer my attention to the base network. And so I'll kind of mitigate the effects of negative transfer, right? So I should point out that we do not change any of the expert networks during the learning here. And both the attention network and the base network are essentially trained by the TD error signal that comes from your decision making here. And there's nothing special that's done to train the attention network. And so we did a bunch of experiments. So we first did a positive transfer experiment just to show that it's more like a sanity check that this thing works. And we then checked for avoidance of negative transfer, and then we looked at selective transfer as well, and we'll just walk through those experiments now. Right? And we trained mostly on a collection of Pong tasks called Pong Soup, and also on a couple of other Atari games. Right? So here is the first experiment. Just like I said, is more of a sanity check. So our expert was like more like a partial expert on Pong that can get about 12 out of 21 points and not a full expert, right? And so the idea is to see, can A to T exploit such an expert and learn faster than learning from scratch, right? And then you can see that obviously that the blue curve, which where you had A to T, certainly did learn much faster and than learning from scratch, which is the green one, right? Just to show that something really happens. So here is the second experiment on negative transfer, where we have two experts. One was an expert on Pong who basically it's not a partial expert, somebody who gets 21 on. And then we had an expert on freeway, which, like Pong, has two actions. You go up or down, right? But the objectives are very, very different, right? And now you can see that learning from scratch, again, is the blue line, right? And the green line is learning starting from the freeway network. You can see not only does it learn slower, but it seems to be, saturating at much lower scores, while learning from scratch does much better. And then suppose I learn with only the freeway expert, which means that I have only a bad expert. You can see that initially, that's the red curve, and initially my agent tries to follow the expert. But once it figures out that the expert is not the right one for this task, it very rapidly goes back to the learning from the base network. And so essentially after a while, it really doesn't have the effects of negative transfer, though initially it does suffer a little bit from that. Of course, the light blue curve here is when I have both the experts, both the freeway and the Pong experts at hand. And so very quickly, once it figures out that the freeway expert is not useful, it immediately switches to the Pong expert and it is able to play at expert level. So this is a very rapid learning. And here's a third experiment on negative transfer, where, of course, we had a perfect agent and a partial expert, and then an anti-Pong expert. So basically, it's going to be really worse. In fact, might be even worse than the freeway expert, right? And so, like the same thing here, the green line, the blue line is learning from scratch. The green line is learning from the anti-Pong, right? And the red line is learning with only the anti-Pong expert and the baseline. This is the A to T with anti-Pong. So again, you can see the same effect. And the purple line is learning with the partial expert and the anti-Pong expert. And the light blue line is learning with all the experts, right? So you learn with the base network, you learn with the partial favorite, you learn with the full favorite, and then you still see that you very quickly latch on to the full expert, right? So this basically, here is the most interesting experiment in my opinion, the selective transfer. So we kind of tried to mimic the backhand forehand example. So what we did was, so when the ball is in, let's say, one half, so when it's the bottom half of the screen, so one expert learns to play, and when the ball goes to the top half of the screen, the ball vanishes, right? So the expert one will learn only the upper half of or upper quadrant here, because you're worried only about 1/4 of the screen when you're in the upper quadrant, and the other expert learns to play only in the bottom quadrant. So essentially, I have two experts: one who is good at forehand, the other one who is good at backhand. Right? And so here you can see what happens. It's a small video that depicts that. So the red line, red bar indicates the attention that's being paid to the top quadrant expert, and the blue bar is the attention paid to the bottom quadrant expert. So you can see that when the ball goes to the top, the upper quadrant expert picks up, right? And the ball comes to the bottom, the lower quadrant expert picks up. So essentially, while the game is progressing, you switch your attention back and forth between one expert and the other. So yeah, so and you can think of learning more complex policies with these. So we have limited our experiments to playing with Pong and some of the simpler Atari games, largely due to computational constraints. But Now people have looked at extending this to other more complex games, and we have some experiments now which we are currently running on Wisdom and a little bit more interesting domains where we can show that not only are you able to do transfer, but you're also able to learn more complex structured policies using the 8OT framework. Right. And the last bit that I'm going to talk about is on learning to multitask by active sampling. Again, this is work done with a master's student of mine and a couple of undergrads, Sahil, Ashutosh, and Parikshit. And this was reported in ICLAIR this year. So the goal here is to do online multitask learning, right? And so, like I said earlier, so there have been other multitask learning work where you try to train, first you train single task networks, right? And then you basically distill their policy onto a single network. And in some sense, you're using supervised learning here, not necessarily RL. And it's computationally intensive because you need to train single task networks. And so what we want to do is not have to do this kind of offline learning for these games first, but try to, do the online learning for the games and then offline copy to a policy network. We would like to do online training onto a single. And so the goals that we had were that they should be able to perform as well as the offline multitask learning methods. But other thing that we set ourselves was because we are trying to do this kind of multitask learning, we should be able to see some kind of data advantage. And so we set ourselves a goal of using only 50% of the training data as would have been required to train each of these games individually, right? And so the way we are going to explain this approach is to start off with a baseline multitasking setup. So I have a set of tasks. Let's say I have K tasks here, and each task has several instances of that. So it could be it's essentially different games, different runs of the same game, right? And what do I do is I first sample a task uniformly, right? And then give it to a network. And then the network learns a policy, right? And the network interacts with the environment and learns a policy. And once a trajectory ends and reach a terminal state, you sample another task uniformly from these K tasks. Once you pick a task, and then you essentially play one of those instances of the task, and you learn, right? So we call this the baseline online multitask learning method, or BA3C, right? And the way we actually modify it is to add what we call a meta task decider, right? So when it is time to resample a task, you don't just uniformly sample one, but you use this kind of an active learning setup, which gives you a sampling distribution based on which you pick what the next task would be, right? And the sampling distribution is going to depend very much on the state of the learning of this multitasking agent. So we proposed 3 different algorithms for the meta task decider. And the idea behind all the 3 algorithms is you maintain some kind of a current performance for the agent, right? And they also maintain what you would like the agent's performance to be. So it could be something that you derive from published scores or the human level play, or it could be as simple as a simple doubling target, right? So it could be a variety of ways in which you could get these targets. And then idea is that you sample the tasks with lower relative performance, so which is AI by TA. So AI is your current performance, AI by target performance. And the lower the performance, relative performance, the higher the probability of you sampling it. Right? That's a rough idea, but then we have different ways in which we go about achieving this. And the reason we needed to do this kind of relative performance is that the scores, the range of scores for all of these games vary very widely, and we wanted to make sure that there's some kind of uniformity across the games, right? And the first one that we used was a very, very direct implementation of the idea, right? And literally there is no learning here for the meta task decider. So I just take the target performance and look at the percentage shortfall right, and call that as MI, right? And then I just use a Gibbs sampler based on the MI to generate the probability distribution, which I will use for sampling my task. So the larger the MI, the higher the probability of the task being picked next for training, right? And remember that you have to keep doing this continuously. That is, so if at some point you just stop doing this and start picking just one game to train on, then you can get into trouble. And the second approach that we did was to treat the task sampling problem as a bandit problem, right? And where the performance, the reward for the bandit, right? So each action here in the bandit is a task that you're going to perform. And if you pick task I, then the reward for that task I is essentially the relative performance of the task. So if the relative performance is very good, then the rewards are going to be less. And the relative performance is poor, the rewards are going to be high. And the goal here is now to pick actions or tasks on which your relative performance is really bad, right? And since this is a non-stationary problem, we use a discounted form of the UCB algorithm, and we can see the results later. This performed really well, right? And the last one that we did was essentially to consider the meta-task decider problem itself as a full RL problem, right? And so the state description for this problem is the fraction of times each task has been sampled so far. Suppose I have n tasks, that's going to be n numbers. And the identity of the previously sampled task, that's just the short-term history, that's one hot encoded. And the previous sampling probability distribution that I had used, right? And this is essentially my state vector. And the actions are obviously the task to sample next. And my reward function is essentially some kind of a weighted average of this relative performance measure over the last 3 time steps. And this essentially gives me some context, just doesn't tell me the immediate performance improvement, but looks at things over a longer window. But the main problem with this approach turned out to be that since I'm treating this as a full RL problem and each sample is one full training episode, for me to generate an episode of this meta-learning problem took a lot of time, right? So given a certain fixed budget for training, there were only so many meta-training iterations that I could run, and hence the learning was slow, right? So here is a summary of the results that we have trained. So we trained this on a set of different games. So you can see that the games are pretty varied and both visually and in terms of the logistics and the goals that they were trying to achieve, right? And so we created what we call different multitask instances. And so each one of these multitask instances consisted of a set of games. And they were sampled arbitrarily from these set of 21 games. So the first 3 multitask instances had 6 games each. And then we had 8, 12, and the last one actually had 21 different games. And so if each one of these games required, say, a million frames to train, then this multitask instance here would have taken 3 million frames of training data. And you would have actively chosen which games would be trained over how many frames, right? It's not like the 3 million frames are uniformly divided between the 6 games, right? And these numbers could be roughly interpreted as what fraction of a single agent's performance do I achieve on this multitask setting. So when they say 0.96, that means that I achieved 96% of the performance of, on average, of the single agents that were trained on each one of those 8 games separately. Right? And now that's actually pretty mind-boggling, given that I only use half the training data for this, and I'm training it on a single network, right? So at MT1 to MT4, we use the same size network as a single game agent, and the last 2, MT5, 6, and 7 use twice the size, if I'm not mistaken. And even when we use 21 games, we're able to achieve a performance of 0.648, right? So BA3C is your baseline agent, which randomly switches, and A5C is the non-learning agent. You can see that on the simpler smaller multitask instances, they do tend to do better. But then the more complex the multitask instances, either the Bandit or the EA4C does better. And I suspect that the EA4C would give consistently better performance only if we could train for much longer. But we didn't want to limit the amount of training data. But here is something that was surprising to us, right? So we looked at the training progress. Here we looked at MT1, and the black line you see is the performance that was achieved by a single game agent, right? So that this is just an agent that was learned to play only Space Invaders, or this is the agent that learned to play only Sequest, sorry. And you can see that in some of these instances, like Demon Attack and Star Gunner, this multitask instances are actually, the multitask learner is actually doing better than the single agent. That I suspect is because some amount of transfer is happening, and potentially that the multitask learner is learning something that is common across these different games, and which I have been half jokingly calling Atari world physics. Right? So it's probably something to do with how pixels move together and so on and so forth that these common layers are picking. Right? And one other thing I wanted to point out is that the random agent, right, tends to, performance tends to drop for the random agent on most of these games, and only in Space Invaders and to some extent in Sequest does the baseline agent even learn. So this essentially means that it's undergoing some kind of catastrophic forgetting. In fact, Demon Attack and Star Gunner doesn't learn at all. But at least in Crazy Climber and Name This Game, it seemed to have undergone some kind of catastrophic forgetting, which you don't see in any one of these active learning setups, because they continuously keep sampling games that require to be learned, right? And so just to understand what was really going on, so we wanted to look at what was really happening. Just because we were over parameterizing the networks, could it be that different parts of the networks actually learn to solve different games? So we were trying to see if there was something like that happening, essentially like different parts of the games network specializing to different games, and there was really nothing that was being commonly learned. Right? And so we essentially called a neuron task agnostic if it is equally responsible for the performance on many of the tasks, and task specific if it is firing only for a small percentage of the games, right? And we just looked at it at the last but one layer before the fully connected layers, the output of the LSTM layer, really. And so we said a neuron is fired for a particular time step if it has an absolute value of 0.3 or more, and we say a neuron fires for a task if the fraction of time steps it fires for while solving a particular task I is greater than 0.01. Okay? So we set the threshold low so that we are making sure that neurons that detect rare events are also counted. Being pretty generous, right? So here is a plot that looks at the activation analysis. So how do you read this? So each of these color dots corresponds to the amount of firing for a specific game, right? And so ignore the color dots for the time being. Just look at the step, right? So a step here essentially means that these neurons here don't fire for any of the games, and these neurons here, I'm pointing in the EA4C plot, fire for one game, and these neurons fire for two, and these neurons fire for three, and so on and so forth. Right? And if you look at the baseline agent, you could see that most of the neurons, nearly 200 of the 250 neurons, fire for either 0 games or only one game. Right? But if you look at the more adaptive ones, right, so you can see that nearly 100 neurons here in A5C fire for more than 2 games. Right? And similarly for UA4C and EA4C, more than 100 neurons fire for multiple games. Right? So this essentially means that there are more task agnostic neurons that are trying to learn something that's more generic across games rather than trying to specialize for single games. Right? And we also did something called the turnoff analysis. We were a little unhappy with the activation analysis because there were a lot of arbitrary things that we picked, like 0.1, 0.3, 0.01, 0.3, and so on. So we want to do turnoff analysis. So if you force neuron outputs to go to 0, how much is the performance affected, right? And so basically what we do is if we force the activation of one of the neurons to go to 0, then observe the change on the individual tasks. Right? So the variance of the column, right, gives a score for the task specificity of the neuron. So if the column is more or less peaked in one game, then you would know that that neuron is specializing only for that game. And if a column is basically more uniformly firing, right, then it's more likely that it is capturing multiple game features, right? So you can see that in BA3C, that a lot of neurons are firing only for one game, right? This is actually just one specific game, not just different games, but just on this one game that most of the neurons fire. That you could also see that there was only one game on which the baseline agent really learned to play well, right? But then if you look at the other approaches, you could see that a lot more variance among the turnoff analysis that indicates that turning off, say, neuron 1 affected the performance on more than one game. So that's basically how to read it. And so we could extend this in many ways. It's very encouraging because we're able to, take a smaller network, but actually, push the learning capacity of the network a lot by doing something very, very simple. And one possibility to extend this is to, force the network to learn more task-agnostic abstractions. Here, we just saw this come out as a side effect, but we could do this more explicitly. And we could improve on the meta task, the episodic task learner by not waiting till the end of the episode to switch tasks, but figuring out a more natural mechanism to switch tasks before the end of the episode. So it shouldn't be too hard, but these are directions that we are trying to push on. So what's next globally? Deep reinforcement learning has really revived the excitement in the RL community. You can see by the cumulative number of papers that have been published. And but there are many fundamental questions still to be addressed. A lot of questions like things like memory, try to learn more about attention, and try and understand how humans do amazingly well in both spatial and temporal abstraction. Right. The goal is to try and move closer and closer to human-like learning with our deep RL setup. Right. So I'll stop here, and you can find out more about our center, the Robert Bosch Center for Data Science and AI, from that URL. Also, links to all the papers that I talked about. Yeah. So there is a question as to are there any code samples to play with, and FiGAR, A to T, and the multitask learning are all available on the GitHub on GitHub. And if you actually look up the papers, which are available off my webpage, there will be GitHub links on the papers as well. And I'll be posting the GitHub links also quickly, very soon on the page. So you have the complete code to play with. Okay. So thank you, folks.